finally, we're going to learn the convention that is really going to take us through the rest of this course and Organic 2. We're going to learn how to draw skeletal structures. And these really simplify how to draw complex organic molecules. So let's start with a fairly simple example, butane. With butane, we have C4H10, and it's a chain of 4 carbons. And it actually takes a little bit of time to write all of that out. In fact, that's why I didn't record writing all of this out, because it takes me some time to write each of those atoms. So how much simpler would it be if we could just represent butane like this? And that's what we can do. Basically, there's a convention here. We draw this chain in a zigzag type structure, which is known as a skeletal structure. And by convention, we have a carbon at each end. So that's what we have here and here. We also have a carbon at each vertex. So that means we have a carbon here and here. So these are our vertex carbons. These are our end carbons. And within this structure, because we know carbon wants to have 4 bonds, we can omit the hydrogens on the carbons and just know how many are present. So the rule is that hydrogens on carbon, and let me underline this, and only on carbon can be omitted in skeletal structures. So if you have non-carbon atoms like oxygen, nitrogen, things like that have hydrogen, you must draw the hydrogen in. So what we can do is assume there's enough hydrogen on each carbon to give it 4 total bonds. So if we look at butane again, and say we're interested in this carbon. Right now, as it's written, you can see that carbon has 1 bond and a second bond, but you know the carbon needs 4 bonds. So that means there's 2 implied hydrogen. There's the 3rd bond and the 4th bond. It's not to say you can't draw them in, because sometimes when we do mechanisms and things later in the semester, I will draw in the implied hydrogen on a skeletal structure just to make it clear, but they don't have to be drawn in. A couple of other general rules. You must draw in heteroatoms. They can't be implied. You have to write them in. Heteroatoms are basically non-carbon and hydrogen atoms. Things like oxygen, nitrogen, sulfur, and the halogens. Second thing is that you must draw in any hydrogen bonded to heteroatoms. So for example, let's take a look at ethanol. And here is, draw out the calculate structure for ethanol, where we have a CH3, a CH2, and then OH. So now what I basically do when I draw this, I see that there's 3 main atoms in the chain, carbon, carbon, oxygen. So when you draw the structure, I draw this. So I have the carbon on the end. I have the CH2 right here. And then next we have the oxygen OH. And what we want to do is we want to tell the reader that at the end of this chain, we have an oxygen, not a carbon. So I write the O in. And then you need to include the hydrogen. You can draw a bond to it, or you can just write it right next to the oxygen. So it would be totally valid just to write it like this. The oxygen took the place of a carbon, so you can say that there's no carbon here. The oxygen took its place. So that's a common misconception sometimes people will make, is to think there's a carbon here and an oxygen. No, the oxygen took the carbon's place. You just have a carbon here and a carbon here. The second rule, you must draw in hydrogen bonded to heteroatoms. So since this oxygen has an H, you have to draw it in. You can't leave it off. Now let's convert this structure into a fully skeletal structure. And just to get an idea of what your zigzag chain is going to be, you're really kind of going from one end to the other. The longest chain you can draw. Let's even give these atoms letters. And when we make this into the structure, we have the Br, so that's A, then we have carbon B, and we form a new bond to carbon C. Now in this case, it's a double bond, so let's just put a double bond in there. Next, we change the angle and go up to carbon D. Then we change the angle and go to not a carbon, but a nitrogen. And I need to draw the hydrogen on the nitrogen, that's E. And then we go to carbon F. You don't need to draw the carbon in, but we need to draw the double bond O and the OH. And the OH is G. So that would be that structure converted into a full skeletal structure. A couple other special cases that we'll deal with on converting to skeletal structures. The first is a ring. Let's say we want to draw this six-membered ring as a skeletal structure. What we want to do is just draw a six-membered ring, which is simply a hexagon. And each of those bends in the ring represent a carbon. Then we need to add any special groups. So we have a double bond here, a double bond here. Usually you draw the double bond on the inside of the ring. Not that it's wrong to draw it on the outside, it's just kind of ugly. We have a chlorine to add here, and then we have two CH3 groups to add here. You can write in the CH3s, or it's totally valid if you want to make it a 100% condensed structure. Just leave it like this, and the terminus of each of these lines is a CH3 group. The second thing we'll look at are triple bonds. So let's say we want to convert this triple bonded structure into a skeletal structure. What a lot of people will do is draw these 5 atoms, 1, 2, 3, 4, 5, right? They're A, B, C, D, and E, and like we did with the double bond, just add 2 pi bonds between C and D. And it's not that this is terrible. I mean, it does represent the right structure, but remember these carbons are sp hybridized and linear. So it's actually more common, or more correct, I should say, to draw the triple bond as a linear entity. And sometimes it's actually easier. So there's my triple bond carbons, C and D. And attached to D in a linear fashion, I'll draw carbon E, and then we have B, and then we'll put kind of a zigzag in the chain to go to A. And even though there's not a vertex here, where the single and triple bond meet, we know there's a carbon there.